Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Continuing our session in tribute to Oliver Atkin, the next talk will be about Oliver and modular forms. And I could say that Oliver loved modular forms. In fact, I think every one of them was one of his intimate friends, and he knew lots and lots about them, in many ways more than almost anyone else. And one of his favorite parts of modular forms were congruences on their coefficients. And Winnie Lee will be speaking about an interesting thing, congruences on non-congruence modular forms. That is, modular forms associated, I gather from the title, to non-congruent subgroups, which are another beast entirely, that's for sure. Okay, here's Winnie.
Thank you very much. I would like to thank the organizers for giving me this opportunity to talk about the other side of Oliver's contribution, which is to the modular forms, as Miller has said. So in this area, Oliver has made a very profound contributions. Here I would just mention two. I'm pretty sure that Professor Birch will say a lot more about Oliver's work. So there's one paper published in 1970 together with Joseph Lehner on the theory of new forms for the group gamma naught n. Okay. So this lays the foundation about the structure of the space of new modular forms for gamma naught n as n varies. And then this theory was later expanded by Miyake for gamma 1 of n. In my thesis, I generalize it to gamma of n, so therefore complete the structure theory about the modular forms. Okay. And the second paper I'd like to mention is published in 1971 by Atkin and Swinnerton-Dyer. And so that one is on the modular forms for the non-congruent subgroups. So that's the subject that I will talk about today, because it's less known and it has lots of computations in it and interesting mixture of computation and theory. Okay. I first met Oliver in 1974 at Harvard when I was a postdoc there. Although we published a joint paper in 1978, and then from 78 to 79, I was his colleague at University of Illinois at Chicago. We did not really work closely together until the last 4 years of his life, from 2005 to 2008. Okay. So during that period of time, we worked on the non-congruence modular forms. So that's what I'll talk about. Okay. So let me start with modular forms in general. So in a nutshell, we say that a modular form is a holomorphic function on the Poincaré upper plane with a lot of symmetries with respect to a finite index subgroup, gamma of SO to Z. Okay. And this group gamma is called a congruent subgroup if it contains a group which is defined using the congruence condition, namely all the matrices which are congruent to the identity mod n for some integer n. Okay. So if gamma is a congruent subgroup, we call the forms the congruence modular forms. Okay. Otherwise, the group is called a non-congruent subgroup, and the forms we call the non-congruence modular forms. Okay. And the congruence modular forms have been studied for over 1 century, and there are many fabulous, fantastic results in that area, including the proof of a Modularity Theorem, which is very closely related to that. And the non-congruence forms, on the other hand, are much less well known and much less understood. Okay. So if we take a finite index subgroup gamma, okay, and that acts on the upper plane by fractional linear transformations. So we look at the orbit space. So that's the upper plane divided by gamma. Okay. So we may compactify it by adding finitely many cusps. Then we get a Riemann surface. Okay. And this Riemann surface is called a modular curve. Okay. And a modular curve has a model which is defined over a number field. Okay. For example, if we take a congruence subgroup, we look at the field of definition of the modular curve. So usually you see that it's defined over Q and sometimes over cyclotomic fields. Okay. On the other hand, Bayes' theorem says that every smooth, projective, irreducible curve defined over a number field is isomorphic to a modular curve. Okay. And actually, there are infinitely many choices for that group gamma. Okay. So now, if you think about this, then you can. This gives you a feeling that SL2Z actually has far more non-congruent subgroups than congruent subgroups. Okay. Even for the curves defined over Q, there are a lot of them which are not congruence curves. Okay. So now, before talking about the non-congruence forms, let me briefly summarize the key results for the congruence forms. So thanks to the talk by Professor Fry and Schoof, so a lot of these things I'm going to say have already been mentioned. Okay, so for modular forms, it comes attached with some parameters. One thing is called a weight, another one's called a level, and also a character. And the theory of new forms says that to study the congruence forms together, all one needs to understand is the arithmetic for new form, okay, with a given parameter. Okay. Now, since the new form is invariant under translation by 1, so it has a Fourier expansion. Okay. Sorry. So this thing moves by itself. Okay. So here I will only consider cusp forms. So the Fourier expansion will start with the term index 1. Okay. And it's a theorem which says that the leading coefficient is non-zero, so we can normalize it such that it begins with 1. Okay. So what we are interested in is to understand the arithmetic of the Fourier coefficients. Okay. So we can view that as an arithmetic function defined on the positive integers n. Okay. So as an arithmetic function in n, the Fourier coefficients of a new form actually is multiplicative. Namely, when the indices mn are coprime, then amn is equal to am times an. Okay. So this says that in order to understand the Fourier coefficients, it suffices to know the those which are prime indexed by prime powers. Then you put together using this formula. So next one we see how the Fourier coefficients vary among the prime powers. Indexed by prime powers. So a new form is an eigenfunction of Hecker operator Tp, okay, and for all the primes p not dividing the level n. Okay. And since we normalize it to start with 1, the eigenvalue of the Hecker operator actually is the pth Fourier coefficient Ap. Okay. So it is on the work of Hecker, which says that this statement is equivalent to saying that the Fourier coefficients actually, it's really very sensitive. Am I going to the wrong direction? No. Okay, so I will come here. So it says that actually the Fourier coefficients satisfy 3-term recursive relation indexed by NP, N, and N over P. Okay, so when the p doesn't when the index is not an integer, that means that term is 0. Okay, so in this recursive relation, we see that the number which is multiplied to an is the pth eigenvalue of the Heck operator, and the constant in front of the last term involves the character, involves the weight. And this relation, well, you can certainly apply to prime power. Then you see how they recurse, how they generate each other. But actually, this works for all n greater than or equal to 1. Okay. For the primes p dividing n, the relationship is simpler. ANP equals to AN times NP. But we are interested in the case that majority, that when the case prime p doesn't divide the level n. Now, because of this theory of Heck operators, one knows that the eigenvalues, which show up as the Fourier coefficients AP, they are algebraic integers. As a result of that, the Fourier coefficients of a new form are algebraic integers. Okay. Furthermore, if we are given a congruent subgroup and a given weight, and so we get a finite dimensional vector space, and that space has a basis consisting of forms whose Fourier coefficients are all integral. Okay. So therefore, if we pick up a form in this space which has algebraic Fourier coefficients, then this form has bounded denominators because it's a finite combinations of the forms with integral Fourier coefficients. So this is a very important feature of the congruence forms. Okay, the bounded denominator property. And a very deep theory in the new forms is the connection with the representations of Galois group. So this is the work of Eichler-Schmura for the case weight k equal to 2 and the Deligne in general. Okay, and actually also the Lenstra when weight k equal to 1. Okay, so this says that well, given a new form G, well, we can find a compatible family of a degree 2 L-adic representations of the Galois group of Q, okay, such that if I fix an L, then that representation is unramified outside of L times the level n. Okay, so if I give myself a prime, well, where it's unramified, so I look at the trace and determinant of the representation at the Frobenius element at P, then we found that the trace is precisely the eigenvalue of Heck operator at P, and the determinant is this chi p times p to the k minus 1. That's the number which is right in front of the recursive relation. So you see this and you see that. So then, okay. So if I rewrite, introduce the characteristic polynomial of the Frobenius at P, then it's equal to t squared minus AP t, well, AP is the trace, plus BP, which is a determinant. So then I can re-express the three-term recursive relation using the coefficients of the characteristic polynomial at P. Okay. So this holds for all the n greater than or equal to 1 and for all the prime P not dividing L and n. Okay. So as a consequence of this L-adic representation, one shows that the eigenvalue of the Heck operator or the p Fourier coefficients of this modular form, well, it's bounded by twice p to the k minus 1 over 2, and this is the so-called Ramanujan-Pedersen conjecture. So this holds for the primes p not dividing n. Okay. So now next, let's move towards the non-congruence forms, which is a much less known area. So let's take a non-congruent subgroup gamma, which has a finite index inside SL2Z. Okay. And we look at the space of curse forms of a given weight k for this group. And this is a finite dimensional vector space. So I consider here the weight is at least 2. And so one can figure out its dimension using the Riemann-Roch, just like the congruence forms. So let's say that the dimension is equal to d. Okay. And just like the congruence forms, any non-congruence forms has a Fourier expansion. Okay, just that the parameter may not be q, but just a root of q. So that doesn't matter. Okay, So here, to make life simple, let's assume that the corresponding modular curve is defined over the rationals, and the cusp at infinity is also a Q-rational number. Okay. So historically, Fricker and Klein were the pioneers for the non-congruence modular forms, and a major contribution came from the paper I alluded to at the beginning, the paper by Atkin and Swinnerton-Dyer, published in 1971, and in 1985, Scholl did also published very important work here. So I will talk about it. Okay. So in their 71 paper, and Atkin and Swinnerton-Dyer talk about several things. So the first thing is about the basis. Okay. I said earlier that if gamma were a congruent subgroup, then we can find a basis whose Fourier coefficients are all integers. So the first difference is that for non-congruence forms, now I cannot find a basis which have integral coefficients. But it's not far away from that. It's integral everywhere except at finite many places. So it's M integral. Okay. And for non-congruence forms, this M actually plays the same role as the level for the congruence forms. Okay. And the biggest difference is that for non-congruence forms, there are no efficient Heck operators. Okay. So let me quickly explain this. Okay. So given any non-congruence group, gamma, we can always find the smallest congruence group containing it. Because it's contained in SL2Z, we just go down from there. Okay. So then this means that any congruence forms which is contained inside the space of non-congruent, the space of weight K forms for gamma should be the forms for the group gamma prime. Okay. So if I take the larger space, that's for the non-congruence group, to the smaller space for the congruence group, then there's a trace map taking from the larger space to the smaller space. And this trace map, when you restrict it to the congruence forms, actually it's not bad. It's a multiplication by a constant, which is the index of the group. Okay. So then if you look at the kernel of this linear map, so those are what we call the genuine non-congruence forms, because it has nothing to do with congruence groups. Okay. Now, Atkin had a conjecture about the Heck operators. Okay. So traditionally, for the congruence forms, the Heck operators were defined using the double cosets. So if we do the same thing using double cosets for the non-congruence group, then Atkin says that if we look at the primes P not dividing this M, then actually the Heck operators defined using double cosets will have the property that it takes all the genuine non-congruence forms to 0. So it doesn't give you any information on the genuine non-congruence forms. Okay. So that's the biggest problem about the non-congruence forms. So Atkin conjecture was first proved by Sayre for the case where the gamma prime is the whole group SL2Z, and the gamma is a normal subgroup of gamma prime. And then Sayre's proof was then finally completed by Berger, I think in 1996. So then now we know that this, there's no efficient Heck operators. So so then what can we say about the arithmetic of the Fourier coefficients of the non-congruence forms? So let me start with I use this as an example, which shows up in the content in the ASD paper. Okay. So let's take elliptic curve defined over Q with conductor M. Okay. So we said that a Bayes theorem tells us that such a E, is a modular curve for some group, finite index subgroup gamma. Okay. Now, for example, if I take the elliptic curve to be the Fermat curve, okay, then in this case, this group gamma can be taken as an index 9 non-congruent subgroup for gamma of 2. Okay. So on this elliptic curve defined over Q, we can consider the holomorphic differential. Okay, so there's only one of them up to constant multiple. So I write it using the uniformizer Q at infinity. So I write it as f dq over Q. So then I see the Fourier expansion times dq over Q. Okay, and the ASD show that actually this coefficients, these ANs, satisfy some congruence relation between ANP, AN, and AN over P. Okay. So in front of AN, we see this number, P plus 1 minus the number of the points of this elliptic curve over the finite field, Fp. And this is a very familiar friend. Okay. Then in front of AN over P, it is P. So, and the congruence, well, the power of P depends on the order of P in N. So if P divides N more and more, and then this congruence will be deeper and deeper. Okay. And so they show that this congruence relation holds for all the prime P not dividing the conductor M, and for N greater than or equal to 1. Okay. So well, we all know that when we look at a holomorphic differential, if I forget about dq over Q, then this F is a weight 2 form, and it's one-dimensional because it's an elliptic curve. Okay. So now, as we look at this number here in front, okay, so now it's a well-known Taniyama-Shimura modularity theorem. It says that there exists a congruence new form, G, well, whose P's Fourier coefficient is this number, P plus 1 minus the number of points over Fp. Okay. So if this group gamma is a congruent subgroup, then actually F is equal to G, and this congruence is equality. It's nothing new. But if this group gamma is a non-congruent subgroup, then this gives a very interesting congruence relation between the Fourier coefficients of non-congruence forms and the Fourier coefficients of congruence forms. Okay. So now let's back to the general case. Okay. So suppose the modular curve has a model defined over Q, and the space of with K cos forms has dimension D. Okay. And we saw before that it has a basis of M integral forms. Okay. So, and based on what they knew about what happens for elliptic curves and also a handful of computational data, so ASD proposed the following congruences for the non-congruence forms. Okay. So, so let's look at a prime P which doesn't divide M. Okay. Now they think that this space should have a p-adic basis. Okay. Because we know that the basis we found, the M integral forms, those are p-adical integral. But they say that there should exist a p-adical integral basis. It may not be the one we found. Okay. Could be a new one. Okay. Such that for each base element, if you look at the Fourier coefficients between ANP, AN, and AN over P, then they should satisfy this congruence condition that we saw before in our previous example. Okay. So, so in front, we have some number AP and the BP. So the mod powers of P, because when we talk about the elliptic curves, then we are dealing with forms of weight 2. In that case, K is equal to 1. So now it's for general case, so you have the multiple K minus 1 in front of it. Okay. So what did I say about AP? So first of all, AP should be an algebraic integer, and with a complex absolute value bounded by the Ramanujan bound, twice of P to the K minus 1 over 2. Okay. And for BP should be P to the K minus 1 times the root of unity. So if this gamma were the congruent subgroup, then I would have, so that means that I have a basis which consists of the Hecke eigen forms, and then I would have equality. Everything would hold. For the non-congruence forms, they think that this should hold true with the congruence replacing the equality. Okay. So the example before is the case that this holds when the weight k equal to 2 and dimension is equal to 1. Okay. And their numerical data also shows that the APs satisfy the Sauter-Tate distribution. So it's very suggesting. Okay. So, but there are some key differences one should keep in mind. So for the congruence forms, we say that if we give ourselves a weight and a group, then we can find a basis consisting of a common eigenforms. But for the non-congruence forms, the basis would vary when P varies. Okay. And the second is that, well, Atkin really thought of this congruence relation, which has exactly the same shape as the recursive relation. In his mind, he would always call this Hj Hecke eigenfunction, although there was no Hecke operator. So this congruence relation replaces the Hecke recursive relation in essence. Okay. And the third one is that, well, where do these APs and the BPs come from? And are there any modularity interpretations? Because they have these properties, which is just like the congruence modular form has. Okay. So let me say a little bit philosophically. The Bayes theorem, well, as we said earlier, that it says that if we just view the non-congruence modular curves as algebraic curves, and they are very general objects because any curves is a modular curve. Okay. So from that point of view, we should not expect something special arithmetic properties. But on the other hand, the ASD congruences suggest that they should have some rules there. Okay. But on the other hand, well, the uniformization of the non-congruence curves by the alpha plane, well, it's quite special. And so this property leads to some surprising consequences. So there's something general, but also there's something special in there. Okay. So ASD paper was published in 1971, and there was no major advances to the subject until 1985. When Shaw came up with this very remarkable piece of work, published, I think, 2 or 3 papers, published in Invenciones. Okay. So Shaw was motivated by the ASD congruences. He certainly wanted, I think, was trying to prove it. So the first thing he did is that he says that to the space of the curse forms, well, which has dimension d, well, he has attached the 2D dimensional compatible family L-dic representations of the Galois group. Okay. And so each representation, rho L, is unramified outside of L times M. Remember that M plays the role of level for the congruence case. So this is this. It's about the same. And it says that for the primes P large enough, okay, and we have the following properties. Namely, the characteristic polynomial at the unramified place at Frobenius P, well, which is a polynomial of degree 2D. He showed that this polynomial actually has coefficient which integral lying in Z, and they are independent of L. Okay. And furthermore, its roots all have the same absolute value, so which is the P to the K minus 1 over 2. Okay. And second, using the characteristic polynomial of his degree 2D representation, he showed a very nice congruence relation, so which has a 2D plus 1 terms, but which is satisfied by all the forms in the space with integral coefficients outside M. Okay, so I regard this as a long congruence relation, 2D plus 1 terms, but which is good for everybody in the forms. While the ASD congruences are finer, they are shorter, they are 3-term congruences, and which should be satisfied by some basis. Okay. So the show representations, its construction is a generalization of the Lin's construction for the congruence forms. So it uses adic cohomology. Okay. And the congruences here, well, arises from the comparing the adic theory to the analogous p-adic de Rham or crystalline theory. Okay. So the congruence actually it follows from comparing the action of the Frobenius of P on the two different space, and they should have the same characteristic polynomial. Okay. So in case that space dimension D is equal to 1, then show congruence well says there are 3 terms, so that's exactly the ASD congruence. So which means that a show theorem establishes the ASD congruence if the dimension is 1. Okay. So in general, to go from the show congruences to the ASD congruences, which is finer, so ideally one would like to factorize the characteristic polynomial, which is a degree 2D. So I would like to factor that as the product of D quadratic factors. Okay, so try to factor it properly. And on one hand, on the other hand, try to find a p-adic basis for the space of such that each base function will satisfy the 3-term ASD congruence with the AP and the BP coming from the factor of the Frobenius polynomial. Okay. So if the group gamma were a congruence subgroup, actually this is achieved by using the Heck operators. Okay, because the Heck operators further break the L-adic space and the p-adic spaces into pieces and establish this. Okay, and for the non-congruence group, there's no Heck operators, so there are no such tools. Okay, that we can use. Okay. So as I mentioned earlier, that the show representations are constructed using the adic cohomology theory. So it's the so-called the motivic. Okay. So according to the Langlands philosophy, they should correspond to automorphic forms for reductive groups. So in this case, that corresponds to the orthogonal or symplectic groups, depending on the weight. Okay. So I think we probably have some feeling that in general, to show that a Gauss representation is automorphic is a very difficult thing. Like the first breakthrough was the work of Wiles, where he proved the Taniyama-Shimura modularity conjecture. So in general, this is very difficult to establish this connection. When show representations does correspond to automorphic forms, we say that, well, its representation is modular. Okay. But in general, the show representation really acts as a link between the non-congruence world and the congruence world because of this Langlands philosophy. Okay. So when the space is one-dimensional, here one actually has a very satisfactory answer. Okay. So earlier, there are some scattered examples, like show proved that for 3 non-congruent subgroups called a gamma 711, gamma 43, gamma 52. So these are the non-congruent subgroups whose weight 4 forms were studied in the ASD paper. Okay. And so these spaces are one-dimensional, and the show actually found the modular forms such that the show representation corresponds to the adic representation associated to these modular forms. And in the paper with Linglong and Zifeng Yang, we also had some examples show that if the weight 3 non-congruence forms comes from the K3 surfaces defined over Q, this also holds. But in general now, thanks to the result by Carre, Winton, Berger, and also Kissing in 2006, that they established the Sayre's conjecture, okay, And now using the various modularity criterion, now one knows that when the space is one-dimensional, then the degree 2 show representations of Galois group are modular. So one knows that. So now this means that when the space is one-dimensional, then we have both the ASD congruences and also the modularity. So this means that in this case, there's a congruence relations between free coefficients of the non-congruence forms and the congruence forms. Okay. Just like what we saw for the elliptic curve case. Now, for the higher dimension, there's no theory which will give us any answers. And so our only hope is to first do some examples. So this is where computation comes in. Okay. So here we start with a congruence group, gamma 1, 5. And from there, we constructed an infinite family of non-congruent subgroups, gamma n, so 1 for each n, as long as n is not 5. So here we have an infinite family of the non-congruent subgroups, and whose modular curves are Q-rational, and this forms as genus 0. And most importantly, the weight 3 curve forms for such kind of groups, we know it's n-1 dimensional, and we also know them explicitly. So there is explicit basis. So then, since we know a basis of the forms, we can use that to check the ASD congruence. Okay. So let me first give you some example when the dimension is 2. Okay. So this here we look at a group which is index 3 subgroup of a gamma 1, 5, and the space is a 2-dimensional. So here I can give you a basis in its Q expansion. So you see that it's integral everywhere except at 3. And the fact that you see that the 3, when the denominator goes up very quickly, so we are convinced that this form has unbounded denominators, which tells you that the group is a non-congruent subgroup. Okay. So since the space is a 2-dimensional and the show representation is degree 4, okay. So in this case, we know the show representation is modular. So actually what happened is that we went to William Stein's webpage to find the possible congruence forms for this to satisfy, and we found them. So those are these forms which with free expansion I gave here explicitly. So these are weight 3, level 27 forms. Okay. And it turns out that if we extend the coefficient field a little bit by joining square root of -1, then the show representation actually decomposes as a sum of the two additive representations associated to these two modular forms. So you see that it's a GL2 plus GL2. Okay. And thirdly, the F plus satisfies 3-term the ASD congruences, with the AP being the P3 coefficient of G plus, and the BP being this character times P squared. And that's the same with F minus and the G minus. Okay. So this example shows a very special phenomenon. Namely, we found a basis, F plus minus, and which satisfied ASD congruences, and which works for all the primes P greater than or equal to 5, which does not vary with P, which works for all P. Okay. So this is the best example one can hope for. Okay. So next, let me show you a case D equal to 3. Okay. So then let's look at the index 4 subgroup. So this weight 3 forms has explicit basis. Well, 3 is dimension 3, so we found the 3 basis element, and which are integral outside 2. Okay. But sitting between this index 4 subgroup and the gamma 1, 5 is the index 2 subgroup, gamma 2. And the weight 3 forms for this group is one-dimensional, and that form should is contained inside S3 gamma 4. In fact, it is H2. Okay. So we knew that in the case that space is one-dimensional, then we have the ASD congruence, then we have modularity. So this we just saw before. So this, in fact, that the modular form is it's a 6th power of the eta function. Okay. So we have the ASD congruences. So this H2 satisfied ASD congruences with this AP coming from the P3 coefficient of this congruence modular form. Okay. So it remains to talk about what happens to the remaining two forms, H1, H3. They generate a dimension 2 subspace. Okay. So here, Oliver did lots of computations. So let me first give you the answer, then we'll go back, look at the forms. Okay. So the answer is that actually we can, well, ASD congruences also holds. Okay. But now that we do have basis, but the basis depends on the residue of prime modulo 8. So we have count to 1, 3, 5, 7 mod 8. So in each case, we can find the basis, okay, with AP and BP. Okay. And if it's count to 1 mod 8, then both H1 and H3 satisfy the same ASD congruences. That means everybody in the space with algebraic coefficients will satisfy the same ASD congruence. Okay. So for the P count to 5 mod 8, H1 and H3 each satisfy ASD congruences, but with opposite AP, and the BP is minus P squared. And for P count to 3 and the 7 mod 8, then we have to go to a linear combinations of H1 and H3. Then again, the APs are the opposites, and the BPs are minus P squared. Okay. So here, Oliver has, from his computation, has identified each AP. Okay. So he has found actually 4 congruence forms: F1, F3, F5, F7. They are expressed using the eta functions. So these are the congruence modular forms of weight 3. And you see from the index and from the Fourier expansion, you see that F1 only consists of the Fourier coefficients, which are count to 1 mod 8, and F3 will be count to 3 mod 8, and so on. Okay. So we go back to the ASD congruence. So in the first set, these APs will be coming from the Fourier coefficients of F1, but we have to tweak it a little bit somehow with plus minus sign. He also gave out the rules. And the same with 3, 5, 7. So they are all multiples of the congruence forms, F5, F3, and F7. Okay. So he found this, but he looked at the BP. He sees that there's a P squared and the minus P squared, minus P squared, minus P squared. So he was very puzzled because with 1 plus sign, 3 minus signs, well, there's no quadratic character of this kind. Okay, so he thought maybe somewhere he made a mistake in his computation. So he went back to check again, but he didn't make any mistake. So which means that the phenomenon here is deeper than what we would think. Okay. And he also showed that this F1, F3, F5, F7, if we do a suitable linear combination, we actually come up with a new form. Okay, if instead of Z, I do 8Z, then this new form will have level dividing 256 and weight 3. Okay, so he really identified these new forms. And if you go back and look at a congruence, you will see that these APs really have a lot to do with the Fourier coefficients of this new form. But there are some little twists in front. Okay. So to explain that little twist, so it's that that little twist comes from a character of the QI, which is the character of order 4. And such a character gives us some weight 1 form. Okay. So the answer about the modularity is that for the group gamma 4, this show representation is 6-dimensional. So we can separate that as the two-dimensional piece and a four-dimensional piece. The two-dimensional piece we saw before coming from the group gamma 2, so we know that we have this new form G2, so that the L function of this two-dimensional piece is the same as L function for the congruence form G2. Okay. For the four-dimensional case, that corresponds to the space generated by H1 and H3, and the associated L function actually is also automorphic, well, except that the form is not what we are familiar with. It's the so-called a form for GL2 cross GL2. So it's so F is the form for GL2, and the other one coming from character is also a form for GL2. Okay. So in this case, because of the numerical data, so one has the target there. So one knows that one should prove that the connection for the modularity. So in this case, we use the Fartin-Sayre method to establish this. So through the computations, Oliver gave all the answers, but our job is to prove that it holds for all. Okay. So then from these examples that I just showed to you, that we're trying to think what is the abstract theory behind it. Okay. So what happens is that in this special case, that in the representation space, there's extra symmetry. Okay. So we characterize this extra symmetry abstractly. That means that in this four-dimensional representation space, there is a quaternionic multiplication acting on that, which means that there are operators Js and Jt, with the square is minus identity, and if you switch the order product, it's -1. So that's exactly the quaternion action. Okay. Now we index these operators by the non-square integers, because these operators comes with it also has some rationality property. Namely, if you look at Js, you find out that Js actually commutes with the Galois representation for the element coming from the Galois group of a quadratic extension. If the element is outside of Galois group of quadratic extension, then it's anti-commuting. You have a minus sign. Okay. So we say that this representation space has a quaternion multiplications over the field Q joining square root of S and square root of T. Okay. So in case of gamma 3, so the show representation has a Qm over the field Q joining root -3. In case of a gamma 4, then the degree 4 piece, well, has a Qm over the biquadratic extension Q joining root -1 and root 2. Okay. So in general, then what can we say? Okay. So this is very recent work, which is completed this year. Okay. So if this Q joining root S root T is a quadratic extension, okay, then the answer is what's shown in the example. Namely, this degree 4 representation decomposes the sum of two degree 2 representations. Each one corresponds to a modular form for a congruent subgroup. Okay. Now, if the group is a biquadratic extension, okay, now it is more interesting. Okay. So sitting inside this biquadratic extension, there are 3 quadratic extensions. Okay. So to each of the quadratic extension, Q joining the square root of S, there is automorphic form, I call the GS for GL2, okay, such that the L function associated to this show representation is the same as the L function associated to that form, or GL2, over that quadratic field. So since there are 3 quadratic fields sitting inside it, so actually there are 3 forms for GL2 over 3 different quadratic fields whose L function agrees with the L function here. So there's lots of symmetry inside this show representation. And actually, this L function also has another way to see it. It agrees with the L function of some automorphic form for GL2 cross GL2. This is what we saw. And using a theorem of Ramakrishnan, representation for GL2 cross GL2 actually automorphic form for GL2 cross GL2 can also be interpreted as form for GL4. So this L function is automorphic, and there are many views to see that automorphicity. Okay. So for this theorem, the proof uses descent and the modern technology, the modularity criteria. Okay. So how about ASD congruences? Okay. So when this Q joining root S root T is a quadratic extension, and we have the ASD congruences, just like the example gamma 3 shows. Okay. And the more interesting part is when it is a biquadratic extension. Okay. So let's assume that this quaternion operator, this JS and JT, they come from normalizers of the group gamma. So they come as a linear combination of the normalizers of group gamma by real algebraic coefficients. Okay. Because as a normalizers of gamma, they also act on the forms. Okay. So to each of U, and I mean S or T or ST, well, we have this quaternion multiplication operator, JU. Okay. And the JU, well, square is equal to minus identity, so its eigenvalues are plus and minus I. So to each eigenvalue, we find the eigenfunction, so in the space, which is I call a FUJ. So, okay. So they form a basis of the space. Okay. Now, on the other hand, we saw before in the previous slides that for each U, there is a automorphic form for GO2 over that quadratic field QU. Okay. So now the two are going to have some relationship. Okay. So what is a relationship? Okay. So if I take a U, so I have this quadratic extension Q joining square root of U. So I know that half of the prime will split in this field and half will stay prime. So I look at those P which splits in this field, Q joining root U. Okay. So actually, for almost all the P, primes P which split in that field, you'll find out that these eigenfunctions that we chose, actually, they have periodical integral Fourier coefficients. Okay. And the ASD congruences holds for such kind of forms at those P which splits in Q joining root U. Okay. So when the congruence holds, then we ask what are the AP and what are the BPs. So AP and the BPs actually comes from the automorphic form that we saw before. So this automorphic form was over this field, and we are looking at the primes above, where P splits. So above P, there are two places. So in each place above P, there is a quadratic factor for that. So there are two such factors. And the coefficients, AUP and the BUP here, are the ones which shows up for the ASD congruences. So namely, in this case, these bases have satisfy the ASD congruences. That means that the Fourier coefficients have a congruence relation with the modular forms, with automorphic forms for GO2 over quadratic extension. Okay. So since these bases are determined from the splitting situation of the primes in quadratic extension, so they can be described using the congruence relation. This is why for the case of gamma 4, we see that it's mod 8. Okay. Okay, so this is what we know about the dimension 2 case. Now, what can we say in general? Okay, so that's back to the general case. Suppose the spatial curve forms at dimension D, and we have this degree 2D show representations, a family of them. Okay. Now, so if I look at the prime P, which is away from this M, okay, I look at L, which does not divide M, okay, which is not equal to P. So then I have this characteristic polynomial, and that characteristic polynomial should have degree 2D. Okay. So we say that the representation is strongly regular at P. If I look at the 2D roots of this characteristic polynomial, I found that half of them are p-adic units, half of them are not. And also those p-adic units are all distinct. Okay. And the other half will be p to the k minus 1 divided by the previous p units. Okay. So Shou has shown that the ASD congruences hold if there's a p, well, if the representation is strongly regular at p. Okay. But if the representations are not regular at p, then the situation is quite different. Okay. So let me show you two examples computed by my student, Jonas Kibelbeck. Okay. So the first example is a curve, which is a hyperelliptic curve, which is a genus 2, defined over Q. Okay. So by Bayes' theorem, we know that this curve is a modular curve with some group gamma. Okay, with a finite index in SO2Z. Okay. So we are going to look at the weight 2 forms for this group gamma. So we know that the weight 2 forms come from the holomorphic differentials. So here he took the uniformizer W as a minus x squared over y, and he found two differentials, dx over y and the x dx over y. He expressed that using the parameter W. Okay. So more precisely, you found that the first cos form is this F1 looking like this, and the second one is F2, which has this explicit forms. Okay. So now you look at the LID representations for the weight 2 forms are just the dual of the Tate modules on the Jacobian. So we have the similar situation. Okay. So I want to show these examples. You see that for the exponent of W here is the multiple of 10, jumps by 10. Okay. And same with F1 and F2. So the coefficients are very sparse. Okay. Now, on the other hand, if you look at this LD representation, for the primes counted 2 and 3 mod 5, actually you see the characteristic polynomial is just t to the 4th plus p squared. So it's very supersingular. Okay. So because these Fourier coefficients are very sparse, so there's no way that you can get a 3-term congruence. So usually when you write down the 3 terms, you'll find out that one term is non-zero and the other 2 terms are 0, which cannot happen. Okay. So this is one case, one example where that in this 2-dimensional space that absolutely there's no forms which satisfy the ASD congruence. For the primes are counted 2 and 3 mod 5. So here is another example, also a hyperelliptic curve with genus 2 defined over Q. Okay, we use the same way to find the forms. Okay, now this case we also have explicit expression for these 2 forms, and now the exponents are odd; they jump by 2. Okay, so they are much less sparse. So if I look at the characteristic polynomial at 3, well, here we write it down here. So you see that, so I want to look at what happens 3-adically. So you see that at mod 3, we get t to the 4th plus t cubed. This tells you that this characteristic polynomial has one root, which is 3-adic unit, okay, which is we call alpha 1. And then immediately you know it has the other root, which is a 3 divided by alpha 1. So it's multiple of 3. Okay. And then there are 2 other roots, alpha 3 and alpha 4. The product is equal to 3, but none of that is a unit. So actually they have 3-adic valuation 1/2. Okay. So in this example, we found that F2 minus 695 F1 satisfy the ASD congruences. Comes from this t minus alpha 3 times t minus alpha 4, this factor of the characteristic polynomial. When you expand it, the constant term is 3, and then you have this A3 coming from this expansion. So this linear combination of F1, F2 satisfied ASD congruences with the A and the B's coming from this quadratic factor of the characteristic polynomial. But on the other hand, one cannot find the second linear independent form which satisfied ASD congruence. So this is a So I've shown you two examples. One example, dimension 2, no form satisfies AST. Second example, dimension 2, one form satisfies AST. So, and certainly we have examples that they all satisfy AST. So that means that in case the strongly regular case that shows us that the AST holds for all. But if it's a super singular case, then situation is very arbitrary. So it is a big challenge to find out what happens in this case. So I would like to end this talk by going back to when Atkin, in this paper, they only propose, they think that this AST congruence would hold, but they never say that they conjecture that this should be true. Okay, and this reminds me of one experience I had in 1975. I went to a U.S.-Japan seminar, which was held at Ann Arbor, Michigan. So Atkin was giving a talk. So on the blackboard, he wrote, "Theorem is a statement proved but may not be true, and conjecture is true but not yet proved." So he is certainly very careful. He didn't call this conjecture. Okay, thank you for your attention.
Are there any questions? Going once, going twice. Okay, let's thank the speaker again.